Hello, my name is Akbar Barkesseh. I'm an electrical engineer. I'm going to have some sort of explanation about the basic rules of differential protection measurement of current in delta Y transformers. I use S Schwarzer Relay 787 SEL to have some sort of validation for the circuits and investigations based on that relay manual. So I'm jumping. You can pause and see what's the agenda here, but I'm going to jump first to transformer winding polarities and in the vector, when we have vector group, how to actually identify the arrangement in the winding in delta side and the polarity of them. At the end of some few slides here, we're going to how to get this arrangement and also the polarities. For example, for YD5 or any of them. So basically, I normally draw delta. That's my way, maybe better ways, but I normally draw delta first and put the value on them based on this ABC capital or small one. Then I draw the Y side phase A, but I'm keeping in mind that anything that you draw in the Y, it should be in parallel with what any one of the sides. That's actually stop you to be confused about how to draw. You don't need to draw very accurately on things. You just need to know that any things that you draw should be in parallel with one side. So for dy1, this one is parallel with this. For yd5, A is in parallel with this. Then we just putting arrow in the same direction of the star side, and then we're writing the winding that is located in this one, which is for A, the A is here, for A is here. And then we draw the rest and write down the windings between each phases in the delta and also the arrows. Then we put the polarity in the arrows to tell us what's the polarity of the windings. Then now we can have the winding arrangement and the polarities in the delta side for different vector groups, dy1, yd5, in between A and B is B or C or whatever. The other things we should actually know about the transformer Y delta is basically the transformer ratio if the value between line voltages. But if you look at the phase conversion between windings, this conversion should be divided or multiplied by a square of root of 3, depends on the case. Then it gives you the transformation between windings. Then basically what we have in the line is this transformation multiplied by the two vector currents subtraction. So basically, in the normal case, these two current 120-degree phase shift, the minus of them is a square root of a square 3 times of each one of them. So they cancel each other, then we're going to have only transformer ratio. And similar here, with the current comes from the delta, we should actually know that whatever we had known about the transformer ratio is about the line voltages. So we're going to have some investigation now about some fault arrangement here. So, for example, I just put right, the polarities and things for a sample vector group is YD7 here, DY1 here, so but it's between B and C is a earth fault, is a two-phase fault, and it's coming here. The current come here. It cannot go only in this winding because equivalent of that, it cannot be only a single winding take care of that. So it's going to be the whole winding. Basically, 2/3 of the current going to this winding and 1/3 is going like that. And then rule of polarity in the B winding here, in the B winding out here, out from C winding here, in C winding in, and the same out here in. So we have this sort of arrangement here when 1/3 if current you want to transfer to this side, it should be divided by transformer ratio if this voltage divided by this voltage, and multiply by square root of 3. Similar here, you see that for two-phase fault in the star side, we have similar situation, different, but the result is same. The current, basically, if this equation is same as this. So this is a typical case that if we have a two-phase fault here, whatever we see in this one, the one phase that see twice of that is see three-phase fault, because the two-phase fault is a square root of 3 divided by 2. A square root of 3 divided by 2 here is basically is half of the three-phase current for each of them, and this one is see the full three-phase current, which is important in coordination between curves, not relevant here. Single phase fault, the same arrangement, only a single winding in the delta will see that, and the ratio is like that, which is tell us the current is almost 58% of the phase current here in this side, because it's divided by a square root of 3. Now we're going to the single phase faults, and in delta side, when we have a grounding transformer, we have an earth fault here coming in the grounding transformer divided by 3, and it's going to use the other healthy phases to distribute this current. And this is how it's distributed when the fault is inside between transformer and delta. And we have the situation in the high side that we have 1/3 current coming is transferred to the high voltage. In this case, as I said, if it's ratio, if this phase to this phase is divided by the ratio and multiply by a square root of 3. So in this case, the fault is outside the zone, outside of actually transformer is between fault and the delta, and this side is no change, only you can see that the distribution of the current compared to the previous one. We have the full current coming out here to go to the ground, but this side is no change. This side we don't have any zero sequence current in delta in this, just in delta, but we have zero sequence current other places. For example, in this area we have zero sequence current. Then so one of the principles of differential protection is what we are going to do with this current. We already been phase shifted, and normally is to no action on one side. Normally that no action is on the delta side. We don't have any action on the readings here, but when readings on the Y side, it should be have some compensations to that to make it correct to go to this side, which are the relay located. In the software, they're using a matrix to compensate these readings in terms of phase shifts and magnitudes. Magnitude is a bit different, maybe look after separately. But I just want to say in this SCR relay, it uses the old-fashioned type and electromechanical relays. It uses kind of a transformer inside the relay as a logic, the same vector group of transformer. When we're reading from Y side, we want to change. We don't want to do any action on the delta side. We want to have some actions here. And that's why I draw in two different colors. So these readings here, there's blue readings up to here, which are located the relays. And this reading is orange, is come again to this point. If these two readings actually in the same direction, then nothing go to the relay, to the differential relay. Now we are going to have some validation of the circuit. In SER manual, to get this compensation matrix, to define that for that reading for delta, it says that you want to not touching any reading in delta, get a fixed delta, but see what's the rotation in the counterclockwise of the A phase to reach to the A phase of delta. So in this case, if there's an example where for dy1, it needs 30-degree counterclockwise to star reach to delta, and this 30-degree divided by 30 is 1. So it uses a matrix they call CTC1, which is these values. I just want to say this value is equivalent of the same vector group transformer, which have the ratio between phases is 1. This k is 1. If k is 1, then the phase coming here, the ratio, the line ratio is 1, is only divided by square root of 3. And we have the rule of polarity that in phase A, out phase A, and the same vector group. And if we write the equations in the delta side, which have been conversion of this star to delta, and we have this KCL equations here, and then make them in a matrix, then we see this matrix, which is similar to this matrix. So it means this electrical equivalent is correct and is used in this relay. And I will say later on why it could not be a unique matrix. And this another example, YD7. They use YD7. It needs to phase A have 5 times of 30 degree to reach to this one, star to delta, and its CTC5 from the manual is this. If you use YD7 with the 1 ratio in the line to line, we get the same value matrix. So what happens if you want to not doing action on the Y side, but doing some action on the delta side readings? In this case, it's equivalent to use in this relay as a kind of an old-fashioned type. Use a vector group of a transformer. We need to give that on the Y side. We need to get input in the Y side, but this is a delta side. I mean that there is a delta Y. Then we should use a transformer to whatever that all been changed from here, it make it reverse back. So it's if it's dy1, it should be yd1 to make that change happen. So it's basically is like this. You have a y delta, and you want to back delta to y. So if you're putting a delta, I mean a star in the delta position and want to back, it's basically changing y delta to delta y with the same number. And this value is exactly in terms of the polarities and arrangement is similar to dy11. So dy1 either could be yd1 or dy11, because we don't care about the star side. It's the delta side, the polarities and arrangement are important. So both of the yd1 and dy11, they have the same type of polarities and arrangement. So why we need to actually do that here? Why you cannot use something from delta to a star directly? And as I said, they are not unique matrices. So if we have something from Y side, we can have in the delta side easily. We can have here Y and work on transformation and then equations, and easily we can get, if we have Y side information, we can easily get the delta side from this matrix. But in the reverse, operation mathematically, when you have y stars, I mean these values, are you capable to introduce easily a matrix to give you the values of this side? The answer is no, because the thing is here we have these inputs and we have the output, but imagine we have these values available from the delta side. Basically, mathematically means inversing this matrix, multiply inversing here and here, then we can have value for the in the reverse. But it's not correct because any all these matrices like this, any of them, they don't have inverse. And the determinant of these matrices are zero, any of them. What does it want to say? That we don't have three equations, three variables. In the delta side, the three currents, the one of them is basically the summation of two of them. So we have two equations, three parameters. So mathematically we have infinite answer for that. You can give any number to any of them and find the other three. That's why in different manufacturer using some sort of very odd matrices, because they may use something in mathematics which are different, then thinking of the stability of the system. That's why, as I said, they are not unique matrices, but in this way, with the vector group, we can actually validate that. Again, for dy1, in manual said now, we want to fix the star and rotate delta in the counterclockwise, so it's 330 degree and it's 11, which is this matrix. Now for dy1 using yd1 vector group with the 1 ratio of the k equal to 1, then we get the same matrix. So it's something to validate this approach. The other thing is mentioned here, and we go to explain about that later on. Any reading from the Y side should have elimination of the zero sequence current. And we're going to explain the elimination of zero sequence current in terms of electrical circuit is something like that, as a closed delta winding and this isolated neutral star here and the reading coming here. So any readings come here include a zero sequence. The out, it doesn't have any zero sequence, and the zero sequence will be taken by the closed delta. It's been the equations here. So with this arrangement, remember there is no connection, isolated neutral here. So when you're writing the equations here, basically you can pause and look at the equations, but at the end this out current is the in current minus zero sequence current for per each phases. So we have this equation. So basically this IA prime is 1/3 of, basically is IA minus zero sequence. I prime B is IB minus zero sequence, and something like that. So, and if you write this equation, the matrix is like this. And if I go to the SEL787 matrix CTC12, which is a filtering for zero sequence, is this. This is exactly like this. Basically it uses, and it says if you want to actually do action on the Y delta side, then you need to eliminate zero sequence current in the Y side. And remember, for this one, with this sort of matrix we introduce here, we automatically eliminated the zero sequence when we did in the Y side and did action on the Y side. because of this arrangement and make it a delta, is already eliminated zero sequence here. But for here, if we just want to get it directly from the Y side without elimination of zero sequence, we have a problem. I'll show you later on. So now we're going to a practical case here. So we want to actually investigate the behavior of the protection, differential protection in the Y delta transformer when we have grounding transformer in the delta side. So basically, just before that, as I explained about the coloring here, in this side is no difference about the scenarios we're going to investigate here. It's just back to where I explained. In this side, we have this current going in the primary side, in the Y side. So it's any current is 1/3 of the earth fault current in the secondary divided by a transformer ratio and multiplying by a square root of 3. I put the same value here, square root of 3 divided by transformer ratio multiplying by the I divided by 3. This I is the earth fault current. And the same transformer vector group that explained over there, in and out this current. But remember, I mean, something before what is going to the secondary. There are some consumption. I mean, something to make it simpler, or which is not make it simpler, which is really in the reality it works. That this criteria, the CT ratio of the delta side divided by CT ratio of the Y side is equal to transformer ratio. What is simplify that? Because if you have I current, I mean in the earth fault current, in the secondary of this CT, this earth fault current divided by CT ratio in delta. I call it I prime in this secondary side. But if I have this equation in place, then I divided by K, which has here, is in the secondary will create I prime as well, because I divided by K by this CT ratio is, and this equation in place, then I have I prime, the same I prime, which I have with this one in the secondary. So long story short, with this condition in place, I divided by K is converted to I prime, and the rest is like this. The current in the polarity, out of the polarity of the CT, and the same for this one, which is like this. And then we know in this matching matrix or matching element, it just will divided by a square root of 3. So a square root of 3 will be eliminated here. If you remember this equations, this coming. So a square root of 3 is eliminated, and then we have into polarity in phase B. So in phase B out of polarity, and when you're having this sort of conversion and with the same vector group here, then we have this blue line and the values 2/3 of I prime coming in, 1/3 of I prime out, 1/3 of I prime out. So that is fixed for all the investigation we're going to have in the rest of this side in building multiple slides. So the first scenario is we don't do any action on the delta readings, but transformer is inside the zone of protection and the fault inside the zone. So these three cities don't see any faults, don't see any current, so zero current coming here, and easily we can see all the three elements of the protection relay will pick up the fault. because there's no current coming from that way, so all the current from this way should go through these protection elements like this. 2/3 here, 1/3 out. So 3 elements will be operated, and it's correct. We want to operate for the fault inside the zone. That's one thing I explained about the influence, bad influence of zero sequence current. Because normally I selected this example because normally we don't expect to have a zero sequence current in the delta. But here, still we don't have zero sequence current here, but for this arrangement that the transformer in zone and the fault out of the zone, then we have two CTs no current, the third CTC the full earth fault current. And this is going to, as I said, is divided by this one is I prime, same as this I prime. It's divided by that, and it's going to coming down, and you see that all of 3 elements will be operated. It doesn't matter any of them operated. It could the differential protection will be operated, but you see that is a operation. The in and out is not match, and then the current going to the differential measurement. This is wrong. We don't want operation of differential element when the fault is outside of zone. And then again, for no action in delta, we see other 2 scenarios: transformer out, fault out. So basically the CT will see 1/3 in, 1/3 in, and 2/3 out. So, and if you're going that is okay, because any nodes we look at, the in and out are there, and no current going to the differential element. So it's no operation of differential, and it's okay because the fault is out. We don't want operation. So again, transformer still is out and fault inside the zone. It will be operated and is okay. We want to be operated, and only one element will pick up the differential, the element in that fault. If you look at that, 1/3 in, 1/3 in, 1/3 in, all of 3 have the same values. So all the 3 current the same value coming here. And then for this node is in and out again, for this node in and out again, for this node the in and out in the same, and going to this, and this how is operated. And that's actually tell us if we have grounding transformer outside the zone, we are okay to not doing any action on the delta reading. But if we have transformer in zone, then we should do some action here. Otherwise, for the earth fault outside the zone, we have wrong operation. That's why instead of not having any action, we put some action here, which is eliminating the zero sequence current. And then we're going to same scenarios. As I said, this side is no change, the blue side. Transformer here, fault in transformer in zone, fault in zone, no current here. Again, the same, no currents, nothing coming here, and this operation is okay. That's the one that has problem in the previous with no action here. We see what happened. We have one current, actually one CTC the current only, and 2 of them nothing. So this current coming here, but what happened here in this delta, it actually subtract the zero sequence current, which is 1/3 of this, and is 2/3 make it this arrangement in this side. So basically is 1/3 is eliminated, and is equivalent to the CTC12 matrix if it's multiplying. And this is 0 minus 1/3 is going to like this, and these polarities are correct here. If you want to have a look, everything here, the polarities. So we see that for each node, the in and out, in and out, in and out, okay, and that's a big help. That show if you're using zero sequence filter, it means using CTC12 matching matrix will fix this problem. And also for the transformer out, fault out of the zone, then we have again 1/3, 1/3 in, 2/3 out. So basically this delta doesn't do anything. We just, this current is transferred this side and there is no operation. Then the last scenario, transformer out, fault in, then the 3 equal 0 sequence current come in, and all of them will be captured by the delta and nothing go out, because it's nothing go out when it's subtracting 0 sequence in each phase, is nothing coming out. So, and it's the operation of the relay and it's correct one. So conclusion from this scenario investigation, that the CTC0 matching matrix, which is no action on delta readings in SER relay, allowable in delta side only when there is no grounding transformer in the differential zone. So if there's a no transformer in differential zone, it's okay to not having any action on the delta reading. But CTC12 matching matrix, a zero sequence filter on delta readings, works well for all ground fault scenarios with grounding transformer located either in and out of the differential zone. So that's how, with some example. I hope that it help you in terms of understanding how differential protection works and these matching matrices. So any questions? This is my LinkedIn here. I would be very happy to have to share my knowledge with you if you have a similar questions or problem in differential protection. Thank you very much, and I hope to be in contact with you. Bye bye.